Okay, so today we will be learning about fundamentals of computing week 2. So this week we will learn about electrical circuits. We'll also learn about transistor. It's not a history lesson, it's more like you should know what it is, how it works, so on and so forth. We'll also be learning about logic gates, and most importantly we will be learning about combinational circuits. Okay, right. So let's talk about electrical circuits first. What is electrical circuits? Almost all of the digital computers use electrical circuits, right? So an electrical circuit consists of two main parts. That is the guy on the inside, who is always a conductive material, right? So it will conduct electricity, and there is an outside layer of non-conductive material, right? So if it's a copper wire, then there is an insulating PVC type of thing that will cover it, right? So how do electrical circuits work? Well, electrical circuit works using voltage, current, and resistance. So this is the equation of how they all connect. So voltage, VOV, right, uh, is essentially, it is a force that designs the, or enables the direction of current, right? I is current or amps, right? That is the the continuous movement of charge, right? Right. And last but not least, R is resistance, ohms. It is the, as the name suggests, a resistance to current movement, right? There is nothing that can move freely. There is always a loss of stuff, right? So this is all there is when it comes to electrical circuits. We should know that V is equal to IR, voltage is equal to current into resistance. So that is all there is about electrical circuits. I know it's so tiny, but anyways, let us keep moving on. Right. So secondly, what we should learn about is the transistor. Now I'm not going to give you the full idea of transistor, the all that kind of stuff. No, I'm not going to do that. So if this is a transistor, it has three inputs. Okay, there is a collector, there is an emitter, and there is a base. All right, so the collector is where current enters, emitter is where current exists, and base is essentially the controller. Okay, so essentially a transistor is a semiconductor, meaning it can become a conductor or an insulator. So it can decide whether it wants to let current go through or not. So if it's a conductor, it is on. If it decides to be an insulator, it is off. This is the simplest version. I would recommend you guys go and look up your own definitions and see how you understand. This is the way I understand this, right? So what it does is it takes the complete current through the collector and takes a small amount of current through the base, right? A small amount, and the base decides whether it is going to on or off, right? So it's essentially, transistor is essentially a tiny electronic switch, right? That is all I have remembered for me. If I am wrong, please correct me down in the comments, but I will not be remembering a lot more of that. I think I've had enough of that in physics. So third one, we have logic gates. That's why we're studying a lot of it, right? So logic gates have two types. Type 1 is combinational circuits. Second, we have sequential circuits. Simplest way to remember this is this guy has no memory. Combinational circuits have no memory. Sequential circuits have memory. So it only has one input at a time, the present input. This one has the input but also past inputs stored. Okay, so that is all there is to this. And as you know that there are so many logic gates, so many logic gates. There's the AND gate, there's the OR gate, there is the NOT gate, and there is the SAND gate, right? There's also the NOR gate, NAND gate, all the logic gates. I think you guys are tired of hearing about all about logic gates and you want something new. Well, don't worry people, I got you covered. The final one is simplification of logic gates. Now, before we do anything, we should ask, why do we simplify logic gates? What's the point? Well, first things first, if we use less logic gates, we can reduce the cost. But that is not the only benefit we can have. We can also reduce the heat that is inside circuits. We can also reduce the space required and put more, much more needed stuff in that place. We can also reduce propagation delay. Now, so in data-driven communication, we learn two types of delays. One is propagation delay and the other one is transmission delay. Propagation delay is length over distance, right? So that is propagation delay. Transmission delay is the bits over total speed, right? So these are the two main delays that we learned in DCN or DNC. Come on, they're both the same. So anyways, back to FC. So this is why we simplify our logic gates. So how do we simplify our logic gates? Well, there are two different ways. One, we can use truth tables, or we can do it mathematically. So using truth tables is essentially we mark all the values and then we draw for each and every single one of them. But we instead of doing that, we can do something called, we can simplify the logic gates mathematically using either Boolean algebra, which we learned in mathematics for computing, or we can use something very interesting known as K-maps. So what is K-maps? Well, forgive me if I'm butchering this, but I think it's Karnaugh maps. So anyways, let's say that you have an input. Let's take AB, right? So what you can do is you can write all of its variables. You can take an F out, and this is an OR gates truth table, right? So what we can do is we can draw a K-map for this table, for this truth table. So when it's a 0 and a 0, it's a 0. When it's a 1, 0, 1, 0, 1, 1, 1. So what you should do is there are some rules that you should follow while using K-maps. So first things first, you should only do like group ones. You should group ones, but you can only do it in multiples of 2, like powers of 2. So it goes 1, 2, 4, 8. So I learned this from the OG tutor, JG, the chemistry guy. I will link his videos down below. But simply put, we can select this one and we can select these two, right? So what we can say is that this one has one constant. So look at this, B and A does not change. So it's A dot B dash plus here B does not change but A does. So since B is 1, this is the equation for F, right? So we can take this and we can simplify it down to A plus B later on using Boolean algebra, but this is a simple idea of how it works. To get a proper idea of how K-maps work, let's take specific a bigger value. Let's take A, B, C, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So I'm gonna apply random values to this. So what I can do is I have to break it into 2. So I'm going to make it A, B and C. So when it comes to A, B, there are 4 inputs. So you would think it will be like this: 0, 0, 0, 1, 1, 0, and 1, 1. But when it comes to K-maps, it's a bit different. It's 0, 1, 1, 1, 1, 0, right? And obviously C only has 0 and 1. So this is the table. And let's try to figure it out. So look at this: A, B both are 0, C is also 0, that's a 1. A, B both of them are 0, C is 1, so that's a 0. A 0, 1, 0, 0, 1, 0 is 1, 0, 1, 1 is 1, 1, 1, 0, 1, 1, 0 is 1, 1, 1, 1 is also 1, right? So finally we have 10, 0, 100 is a 0, and we have 1, 0, 1 is a 1. So as per the rules, you can't circle 3s, 2 pairs of 3s. That is not right. You can do something like this. You cannot also go diagonally. It should always be horizontal or vertical. So what do you think is the best way to do this? Well, we can do a 4, a 1 and a 1, right? So if we do a 4, let's take the first circle. So here in all of these, right, let's see who is the guy who remains constant. So as you can see, A changes, so we can't take it. B also C also changes, so the only person who remains constant is B, so we can simply put B. Let's consider the other one. Since it's only one of one circle, we can put all the values in there. So A dash B dash dot C plus A is 1, B is 0, C is also 1, so I can put A dot B dash dot C. This is this table written as an equation. Now something with JG chemistry JG chemistry tutor did not specifically say, I haven't seen him say it anywhere, is how you can fold a K-map. Now let's say you have A, B, and then you have C, D, right? So if you're wondering that if a K-map can only have maximum 4 variables, well, you can break. If you have 4 variables, you can do like this, but if you have 5 variables, well, you can make a fifth one of only C, oh sorry, only E of the fifth variable, or you can then break it into pieces. So that's how you do it. Just saying an extra little tidbit. But anyways, if you have something like this 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0, now why do you think that all like we are writing in this specific order? Well, it's because all the ones are clumped together. Look at this. So what you can do is you can loop back around stuff, right? You can connect it. So it's like it's like a torus or a donut of sorts. So how you can connect it is like this. Say you have, I'm gonna write this in blue, 1 1 1 here, right? What you can do is you can connect these guys like this, right? You can connect these guys like this. Similarly, you can also connect them on top, right? Top to bottom. You can fold the paper so that they connect like this, right? So that is also one of the ways that you can use K-maps. So I recommend you practice a little bit with K-maps. This is how you use K-maps. I have not I'm gonna admit I haven't explained it in a great detail, so I'm gonna link the guys who helped me study this down in the description. So anyways, that is all for FC week 2. In labs, what we learned was mainly Arduino, and one more thing that we learned during labs, which is resistors. So resistors are of two types. You have 4 bands, or you want to get 5 bands. Now there's a color scheme that that simply goes from 0 to black to 9 white, right? So there are some colors here with the color scheme. I don't think they expect you to remember that, but what they might expect you to remember is how these are all classified, right? So to give you a simple overview, always start from right to left. So the last band will always be something known as a tolerance band. So tolerance band will be from +1, plus or minus 1%, plus or minus 2%, to 3, 4, 5, and then anything else that doesn't have a color has, I think, 0 or 20%, right? Then you will have something known as a multiplier, right? So again, 0 means 0, 0 means 1, that means just 1. 1 means it's 10 to the power 1, 2 means it's 10 to the power 2, so on and so forth. And if it's 4 bands, whatever number that comes here, it's considered as simply digits, right? And if it's 5 band, it will simply also be considered as another digit, right? This is how you find the resistance of a resistor using the bands that are in the resistor. Okay, anyways, that's all for this week. Have a great day.